When ancient storytellers gathered beneath the trembling glow of oil lamps, they often spoke of the sky as if it were a living being, a colossal spirit whose moods shaped kingdoms and carved destinies into stone. And it is in the cadence of those old voices that the story of weather truly begins, not as a cold scientific concept, but as an eternal companion of humankind, a force both feared and revered, weaving its way through the chronicles of civilizations. Long before the first scribes pressed styluses into wet clay, early hunters learned to read the heavens with instincts as sharp as their tools, sensing shifts in the wind through the rustle of grass, noticing how the low flight of swallows foretold rain, and tracking the shimmering haze rising from the earth that warned of the day's sweltering heat. These small observations, collected over generations, formed the first proto-science of weather, long before anyone could imagine barometers or satellites, long before thunder could be separated from the mythic footsteps of gods. In the fertile valleys between the Tigris and Euphrates, where the Sumerians shaped the earliest cities out of mud brick and hope, weather determined everything from crop cycles to the survival of entire communities. The annual flooding that nourished their fields did not follow the punctual predictability of the Nile. Instead, it arrived with a temper as volatile as summer storms. The priests of Ekur, temple watchers with eyes trained on the horizon, kept meticulous records of cloud formations and winds, seeking patterns in nature's caprice. Their tablets show the earliest attempts at understanding atmospheric rhythms, describing the warm, dust-laden gusts known today as the shamal, a northwesterly wind that could rise without warning, choking the streets with sand and halting caravans for days. Even then, people understood that the invisible currents circling the globe were not random, but part of a vast, interconnected dance linking distant lands through unseen threads of air. Far to the west, the Egyptians crafted a different relationship with the sky, one shaped by the gentle regularity of the Nile's floods and the desert's relentless sun. To them, weather was not a mystery, but a cosmic order, a celestial mechanism maintained by the gods. Ra's solar barge crossed the sky each day in a journey so steady it became the backbone of their calendar, and the whispering winds of the Mediterranean brought the cool breath of foreign seas into the heat-stricken delta. Yet even in this land of apparent stability, ancient observers noted peculiar atmospheric anomalies. Records carved into temple walls tell of red-tinged rains falling from dust-heavy clouds, likely colored by Saharan sediments carried thousands of kilometers before mingling with moisture high above the Nile Valley. The desert did not respect borders. It drifted silently on rising thermals, shaping weather far beyond its own horizon. For a civilization so attuned to cycles, these rare events were ominous signs, stirring murmurs among priests who felt the sky was trying to speak in a language older than ritual. In the Aegean world, Greek philosophers began to unravel the mysteries of weather with methods that strayed from divine explanations. Thales, who gazed at nature with a curiosity that transcended myth, believed that water was the fundamental substance of the universe, an idea that echoed through his interpretations of rain, clouds, and storms. His successors, including Anaximander and Anaximenes, proposed that air itself was a primordial element capable of transformation into fire, water, and earth. Yet it was Aristotle who gave weather its first systematic examination in Meteorologica, a text that would dominate scientific thought for nearly 2 millennia. Aristotle envisioned the atmosphere as a series of layers, each governed by distinct principles, and although many of his conclusions were incorrect, his determination to classify and describe atmospheric phenomena marked a turning point in human understanding. He cataloged everything from halos around the moon to the formation of dew, and his explanations, poetic yet earnest, reflect a mind striving to impose order on a world that refused to be tamed. Meanwhile, in China, scholars of the Shang and Zhou dynasties interpreted weather through a blend of observation and cosmology. Oracle bones bear inscriptions of royal inquiries about rain, storms, and seasonal changes, indicating the deep significance of atmospheric conditions in agricultural planning and military strategy. By the Han Dynasty, the Chinese had developed sophisticated instruments such as the earliest known weather vanes, crafted in the shape of birds or mythical creatures perched atop palace towers. They also recognized the connection between barometric pressure and bodily sensations long before the existence of barometers. Ancient texts describe headaches and joint pains occurring before storms, subtle observations that reveal an intuitive grasp of meteorological cause and effect. The Chinese concept of qi, an invisible flow of energy permeating all things, aligned curiously with the modern understanding of air currents, even if it was framed in spiritual rather than scientific terms. Across the oceans, the Maya of Mesoamerica studied the sky with an intensity rivaling that of any Old World civilization. Their priests, who doubled as astronomers, understood the importance of seasonal rains with a precision born of necessity. The Yucatan Peninsula, lacking major rivers, depended heavily on the capricious arrival of the wet season, and the Maya tracked atmospheric signs with exceptional care. They noted the shifting winds heralding the onset of the monsoons, recognized the towering anvil-shaped cumulonimbus clouds that signaled approaching storms, and tied these observations to their complex calendar systems. In their art, the rain god Chak wields lightning as an axe, an emblem linking atmospheric electricity to divine power. Yet beneath this mythic imagery lies a deep empirical awareness of how thunderstorms shaped their world. Their agricultural cycles, architecture, and even political power were bound to the sky's unpredictable offerings. While the Maya watched the heavens from jungle temples, the Polynesians were reading the open ocean like a vast manuscript of winds and waves. Their voyages across the Pacific required an intimate understanding of weather patterns over unimaginable distances. Navigators trained from childhood learned to read the swell patterns that radiated from distant storms, often hundreds of kilometers away, and could feel subtle shifts in wind direction through the pressure of the sail ropes against their hands. They recognized the towering clouds that formed above remote islands, using them as markers when land lay beyond the horizon. To them, weather was not merely a daily inconvenience or blessing. It was the very medium through which they carved paths across one of the most formidable environments on Earth. Their mastery of wind and sea remains one of humanity's most astonishing achievements, a testament to the profound wisdom that develops when survival hinges on understanding the moods of the natural world. In medieval Europe, weather held a different kind of authority, its whims often determining the fate of harvests that stood between prosperity and famine. Chronicles from this era describe winters so harsh that entire rivers froze solid, allowing carts and horses to cross where boats once sailed. The most dramatic of these events occurred during the period now known as the Little Ice Age, a centuries-long cooling that reshaped landscapes and livelihoods. Glaciers in the Alps advanced relentlessly, swallowing villages and crushing forests beneath their creeping weight. The Baltic Sea iced over so thoroughly that traders established temporary roads across its frozen expanse, noting with both awe and dread the colossal stillness of waters usually roiling with storms. Even the River Thames in London froze repeatedly, giving rise to frost fairs where merchants set up shops on the ice amid the bitter cold. These events were not just curiosities, they dramatically altered agriculture, migration patterns, and political stability, illustrating how even slight shifts in global temperature can cascade into monumental societal transformations. But while Europe battled cold, the Indian subcontinent synchronized its entire cultural and economic rhythm with one of the most astonishing weather systems on Earth, the monsoon. For thousands of years, farmers, merchants, and poets alike awaited the arrival of the southwest monsoon winds, watching for the first darkening of the sky over the Arabian Sea. The monsoon was more than rain. It was a life-giving pulse that sustained millions, dictating planting seasons and influencing trade routes across the Indian Ocean. Ancient mariners learned to harness these predictable winds, using them to travel between Africa, Arabia, and India with remarkable efficiency. And the monsoon became the backbone of transoceanic commerce. Yet its power was double-edged. Chronicles speak of years when the rains failed, bringing devastating drought, while in others, the deluge was so immense that entire settlements vanished beneath floodwaters. The monsoon's breath shaped empires, and its absence toppled them. Its presence woven into every aspect of life, from architecture to mythology.
While monsoons defined the Indian Ocean, the Atlantic held its own terrifying phenomenon: hurricanes. Indigenous Caribbean societies had long understood the destructive potential of these spiraling giants, giving them names that captured their ferocity. When European explorers first encountered these storms, they were unprepared for the sheer scale of the devastation. Ships were hurled onto shores like toys. Settlements were torn apart in minutes, and the survivors often wrote of the sky transforming into a monstrous vortex, as if the world itself were being unmade. Early meteorologists struggled to comprehend the structure of these storms. Without satellites or aircraft, their understanding came only from shattered remnants of ships and the scattered testimonies of terrified witnesses. Yet over time, patterns emerged. Mariners learned to recognize the deceptive calm of the eye, the violent wall of winds surrounding it, and the long spiral rain bands stretching like arms across vast distances. These observations laid the groundwork for the first hurricane tracking methods, turning raw fear into a primitive form of preparedness. Across the deserts of North Africa and the Middle East, another atmospheric force shaped cultures with equal ferocity: the hot, dry winds known variously as the Khamsin, the Sirocco, and the Harmattan. These winds could rise suddenly, sweeping across dunes with such intensity that travelers reported a sensation of the skin itself evaporating beneath their breath. They carried fine dust that infiltrated every crevice of homes and markets, turning skies a coppery red and giving the sun a distorted, ghostly appearance. Ancient physicians noted how these winds affected human mood and health, causing headaches, irritability, and fatigue, symptoms now recognized as responses to sudden drops in humidity and spikes in temperature. Caravans crossing the Sahara relied on experienced guides who could interpret small changes in wind patterns, knowing well that a misjudgment could lead to disaster. These winds, though feared, were also woven into cultural identity, their arrival marking transitions between seasons and shaping agricultural practices along the desert's edge. Across the vast steppes of Central Asia, weather served as both ally and adversary to the nomadic tribes who shaped the fate of continents through their ceaseless migrations. For the Scythians, Sarmatians, and later the Mongols, the sky functioned as an unwritten chronicle, its patterns guiding their herds and determining the rhythms of their seasonal wanderings. These mounted peoples understood the subtleties of atmospheric change with a precision born of necessity. They recognized the pale, milky halo around the moon that warned of approaching storms, and they interpreted the faint scent carried in cold northern gusts as the harbinger of early winter. It was said among Mongol riders that the wind speaks first, and their uncanny ability to anticipate weather shifts contributed greatly to their legendary conquests. Chroniclers noted that Genghis Khan often planned campaigns based on the expected behavior of winds across the Asian plains, favoring seasons when storms would hamper enemy fortifications while the steppe horses thrived in brisk, dry air. Thus, the weather itself became an invisible strategist, shaping the campaigns that altered the balance of Eurasian history. Farther north, the Norse seafarers faced a domain where weather ruled with iron authority. The North Atlantic, unpredictable and unforgiving, demanded an understanding of wind and wave that bordered on the supernatural. Viking longships, narrow and flexible, were marvels of engineering, but their true power came from the mariners who could read the shifting texture of the sea. Saga literature is filled with descriptions of eerie fog banks that rolled across the ocean without warning, thick enough to swallow entire fleets, and of sudden squalls that struck with a violence capable of splintering masts in moments. These early explorers learned to navigate not only by the stars, but also by subtle atmospheric clues. The color of the sky above the horizon, the smell of distant rain carried on gusts, the faint shimmering of air above the water that signaled changes in temperature. Their voyages to Iceland, Greenland, and even North America were made possible by this intimate relationship with the elements. For them, the weather was less an obstacle and more a mercurial companion whose moods they carefully courted. As Europe emerged from the medieval world into the dawn of the Renaissance, interest in the mechanics of weather deepened, driven by both curiosity and crisis. The 16th and 17th centuries saw dramatic climatic fluctuations, episodes historians now associate with the tail end of the Little Ice Age. These changes manifested in bitter winters, failed harvests, and erratic storms, inspiring scholars to search for a rational understanding of atmospheric behavior. It was during this period that the first modern meteorological instruments appeared. In 1643, Evangelista Torricelli introduced the mercury barometer, a simple yet revolutionary device that allowed scientists to measure air pressure for the first time. Torricelli famously remarked that we live submerged at the bottom of an ocean of air, a poetic observation that reframed the atmosphere as a tangible medium rather than an invisible void. Over the following decades, Inventors created thermometers, hygrometers, and rain gauges, transforming weather from a matter of intuition to a field of quantitative study. Yet even with these tools, the atmosphere's complexity remained elusive, a puzzle assembling itself slowly with each new discovery. Meanwhile, in Japan, the Edo period fostered a unique culture of atmospheric observation. Scholars and artisans kept detailed records of weather phenomena, often blending scientific curiosity with artistic sensibility. Ukiyo-e prints depicted dramatic rainstorms with slanted lines capturing the intensity of wind-driven rain, while haiku poets distilled the essence of seasonal change into sparse, evocative imagery. At the same time, Japanese fishermen and farmers relied on centuries of practical knowledge. They recognized the distinctive clouds preceding typhoons and developed architectural features such as flexible wooden frames to withstand the immense.
Across the Indian Ocean, the Arab world became a center for meteorological thought during the Islamic Golden Age. Scholars such as al-Farghani and Ibn Sina expanded on Greek ideas while making significant original contributions. They cataloged wind patterns across the Red Sea and the Gulf of Aden, recognizing recurring seasonal behaviors and documenting them with meticulous care. Mariners who sailed between East Africa, the Arabian Peninsula, and India depended heavily on this knowledge, using star positions and wind cycles to guide their journeys. The famous navigator Ahmad ibn Majid compiled extensive treatises describing the monsoon system, ocean currents, and cloud formations, blending practical seamanship with scientific rigor. His writings influenced explorers for centuries, emphasizing the interconnectedness of weather across continents and oceans. To these scholars, understanding the atmosphere was not merely academic, it was essential for commerce, exploration, and cultural exchange. In the Americas, indigenous nations cultivated their own sophisticated systems of meteorological understanding long before European contact. The Plains tribes of North America, living under vast open skies, became expert interpreters of clouds and winds. They recognized the towering cumulonimbus formations that signaled the approach of supercell thunderstorms, some of which could give rise to tornadoes, phenomena especially common in the area now known as Tornado Alley. Their oral traditions describe spiraling winds with a mixture of awe and caution, and their survival often depended on reading the subtle cues that shaped the violent weather of the Great Plains. Farther south, Andean civilizations developed distinct atmospheric knowledge shaped by altitude. In the highlands, where thin air sharpened every breath, people observed the way clouds clung to mountain peaks, predicting rain based on the behavior of mist swirling around jagged summits. Their terraced agriculture depended on such insights,
revealing a deep harmony between human ingenuity and the towering forces of nature. By the 18th century, meteorology began to crystallize into a systematic science, driven by the Enlightenment's emphasis on reason and empirical observation. One of the era's defining figures was Benjamin Franklin, whose curiosity about lightning led him to conduct his famed kite experiment and act as daring as it was dangerous. Franklin was fascinated by the nature of thunderstorms, and his work ultimately revealed that lightning was a form of electrical discharge, forever altering humanity's understanding of atmospheric electricity. His invention of the lightning rod saved countless structures from destruction, marking one of the earliest instances in which scientific insight directly mitigated the dangers of weather. At the same time, observers across Europe and America began establishing networks of weather stations, sharing data through increasingly rapid communication channels made possible by improved postal systems and later the telegraph. For the first time in human history, it became possible to track storms in something approaching real time, a profound shift in how society.
In the 19th century, a new technological marvel transformed meteorology: the telegraph. With this invention, weather observations could be transmitted across vast distances within minutes, enabling scientists to create the first synoptic, meaning simultaneous, weather maps. These maps revealed the large-scale structure of atmospheric systems, including the presence of high and low pressure areas, fronts, and storm tracks. Men like Admiral Robert Fitzroy, best known for commanding the HMS Beagle during Charles Darwin's voyage, became pioneers of modern forecasting. Fitzroy established one of the earliest national weather services and introduced the term weather forecast, a concept previously unimaginable. Despite resistance from some who viewed attempts at prediction as presumptuous, an intrusion into what they believed was divine territory, Fitzroy persisted, convinced that understanding the atmosphere could save lives. Although his early forecasts were imperfect, they marked a new era in which humans attempted not only to observe the weather, but to anticipate its future behavior. Yet, while forecasting advanced, nature continued to deliver reminders of its overwhelming power. Nowhere was this more apparent than in the 1883 eruption of Krakatoa. When the volcano exploded with unimaginable force, it propelled ash and aerosols high into the stratosphere, altering global weather for years. Temperatures dropped worldwide, and vivid red sunsets inspired artists across Europe and America, including perhaps the famously eerie skies in Edvard Munch's The Scream. Scientists later recognized that volcanic eruptions could have profound climatic effects, underscoring the complex interplay between geological and atmospheric forces. Krakatoa was not the first such event. Tambora's eruption in 1815 produced the Year Without a Summer, but it occurred at a time when global communication allowed people to compare observations. deepening the understanding that weather was part of a planetary system. As the 20th century dawned, technological innovations surged forward with unprecedented speed. The Wright brothers' first flight in 1903 opened the skies to human exploration, and within decades, aircraft became indispensable tools for meteorology. Pilots reported turbulence, cloud formations, and temperature changes at altitudes previously inaccessible to observers. During World War II, the need for accurate weather information became critical, influencing military strategy on a global scale. The timing of the D-Day invasion hinged on meteorological forecasts predicting a narrow window of passable conditions in the stormy English Channel, illustrating how weather could become a decisive player in human conflict. Meanwhile, scientists were beginning to use high-altitude balloons to measure conditions in the upper atmosphere, revealing the existence of the jet stream, fast-moving rivers of air that circle the planet and shape weather patterns across continents. The discovery of these winds revolutionized aviation and forecasting alike, providing a new lens through which to understand the movement of storms. As meteorology entered the mid-20th century, the sky itself became a laboratory, and the tools humanity devised to study it grew increasingly sophisticated. In 1946, a small team of scientists successfully triggered the first artificial snowfall by dispersing silver iodide particles into clouds over Mount Greylock in Massachusetts. This early experiment in cloud seeding marked the beginning of deliberate attempts to influence weather, a concept that felt almost mythic in its implications. Although the effectiveness of such techniques remains limited and sometimes controversial, the idea that humans could interact with clouds at a chemical level signaled a profound shift in the relationship between civilization and the atmosphere. The sky was no longer an untouchable realm. It had become a domain of experimentation, its mysteries approached with instruments as complex as the storms they sought to decode. At the same time, the Cold War spurred rapid advancements in atmospheric science, driven by both civilian and military motivations. Understanding weather became essential not only for agriculture and transportation, but also for predicting the behavior of radioactive fallout, tracking missile paths, and operating the growing fleets of aircraft that crisscrossed the globe. High-altitude research balloons reached into the stratosphere, carrying instruments that measured ozone levels, cosmic rays, humidity, and temperature at altitudes never before explored. These data revealed striking truths about the upper atmosphere, including the existence of the ozone layer, whose fragile chemistry would become one of the late 20th century's defining environmental concerns. The atmosphere, once perceived as boundless, proved to be far more delicate than assumed, a thin, shimmering veil around Earth, dynamic yet vulnerable, capable of absorbing sunlight and shielding life, but susceptible to even small chemical disturbances. Then in 1960, a technological leap occurred so momentous that it changed meteorology forever. The launch of TIROS-1, the world's first successful weather satellite. For the first time, humans could look down upon Earth's atmosphere from above, witnessing cloud systems sprawling across continents like vast, swirling works of art. Images transmitted from orbit showed hurricanes unfolding their spiral arms with haunting precision, revealed the patterns of cold fronts sweeping across oceans, and captured the seasonal transformations of land and sea. This celestial vantage point transformed forecasting from a largely regional discipline into a global one. No longer were meteorologists limited to observations from scattered ground stations. They could now watch storms develop in real time as they roamed the planet. The view from space exposed the interconnected nature of weather, demonstrating that a disturbance in the Pacific could, days later, influence conditions in North America, Asia, or beyond. These revelations marked the beginning of true global weather awareness, a perspective that profoundly shaped scientific understanding and international cooperation.
Yet, even with satellite imagery, many atmospheric mysteries persisted. Tornadoes remained particularly elusive. Formed within violent supercell thunderstorms, these rotating pillars of wind often emerged and dissipated with little warning, leaving devastation in their wake. Throughout the mid-20th century, researchers in the American Great Plains chased storms in modified vehicles, armed with instruments designed to measure wind speeds, pressure drops, and rotational structure. Their work, often undertaken at great personal risk, produced groundbreaking insights into how tornadoes formed and evolved. One of the most dramatic breakthroughs occurred in the 1970s with the deployment of Doppler radar technology. This innovation enabled meteorologists to detect the internal rotation of storms, mesocyclones, before tornadoes touched down, significantly improving warning times. The atmosphere, once inscrutable in its swift violence, had begun to reveal its hidden rhythms, although it continued to guard its most turbulent secrets fiercely. Meanwhile, the study of weather expanded beyond Earth itself. As spacecraft ventured toward other planets, scientists realized that atmospheric science was not confined to a single world. Mars, with its towering dust storms that can engulf the entire planet for weeks, demonstrated how thin atmospheres can still create dramatic meteorological phenomena. Venus, cloaked in suffocating clouds of sulfuric acid, revealed winds that circled the planet at hundreds of kilometers per hour, moving far faster than the solid surface beneath them. Jupiter showcased storms of almost unimaginable scale, including the Great Red Spot, a vast anticyclonic storm larger than Earth and possibly centuries old. These extraterrestrial climates offered new perspectives on atmospheric dynamics, helping scientists refine models that ultimately deepened understanding of our own planet. Weather, once considered a local or terrestrial concept, expanded into a universal force shaped by chemistry, gravity, and solar energy in ways both familiar and astonishingly alien. Back on Earth, the latter half of the 20th century saw meteorology woven increasingly into the fabric of everyday life. Television broadcasts brought forecasts into living rooms, translating complex atmospheric data into friendly symbols and maps. Aviation relied heavily on precise weather predictions as jet aircraft soared through the newly understood jet streams, carving rapid paths between continents. Farmers used forecasts to plan irrigation, planting, and harvesting on a scale unimaginable to their ancestors. Shipping routes adjusted to avoid storms whose trajectories could now be predicted days in advance. Weather services expanded globally, creating international networks that shared data across borders, recognizing that the atmosphere respected no political boundaries. This era marked a democratization of meteorological awareness, turning knowledge once confined to scholars, mariners, and priests.
Yet the atmosphere also revealed new challenges. The 1980 eruption of Mount St. Helens sent volcanic ash soaring into the stratosphere, eye-opening in its destructive power and its ability to cripple air travel. The eruption highlighted how fragile aviation could be in the face of airborne ash, which could melt inside jet engines and render them useless. Suddenly, meteorologists were tasked with tracking not only storms, but clouds of fine particulate matter drifting across continents. Lightning, too, demonstrated its unpredictability, with scientists discovering that volcanic plumes, dense with ash and charged particles, could generate lightning storms of extraordinary intensity, an atmospheric phenomenon simultaneously terrestrial and volcanic in origin. Another turning point arrived with the 1987 Great Storm in the United Kingdom, a tempest so powerful and unexpected that it spurred major reforms in forecasting practices across Europe. The storm demolished forests, toppled ancient trees that had witnessed centuries of history, and shocked a public long accustomed to mild, predictable weather. Although modern forecasting tools existed, the event demonstrated how even small errors in interpreting atmospheric models could lead to enormous societal consequences. The atmosphere reminded humanity that it was still capable of surprise, despite all advances in science and technology. By the late 20th century, computing power revolutionized meteorology yet again. Numerical weather prediction models became increasingly sophisticated, using complex equations to simulate atmospheric behavior with unprecedented accuracy. Supercomputers ran millions of calculations per second, integrating data from satellites, weather balloons, aircraft, and ocean buoys
into intricate simulations of Earth's atmosphere. These models revealed the delicate interplay between oceans and air, highlighting the immense influence of phenomena such as El Niño and La Niña, whose oscillations in Pacific Ocean temperatures reverberate through global weather systems. Scientists began to understand that the oceans and atmosphere formed a single, intertwined engine, driven by sunlight, shaped by planetary rotation, and influenced by countless feedback mechanisms. The complexity of this system defied simple explanation, yet the models grew ever more capable of capturing its rhythms. The beginning of the 21st century ushered in an era where meteorology and technology became inseparable. Satellite constellations multiplied, offering high-resolution images of storms from multiple angles. Weather radars grew more sensitive, able to distinguish between rain, hail, snow, or even insects or dust swirling in the air. Mobile phones transformed the distribution of forecasts, turning every citizen into a potential observer through crowdsourced weather reporting. Drones began to explore storms from within, sending back data from regions too dangerous for aircraft. The atmosphere was being measured, analyzed, and understood with a granularity never before imagined. Yet for
As the unfolding century pressed forward, new layers of atmospheric understanding emerged from the convergence of disciplines once considered separate. Climatologists, oceanographers, and atmospheric physicists began working together more closely than ever, uncovering patterns and cycles that had remained hidden over millennia. Ice cores extracted from Greenland and Antarctica revealed bands of ancient snowfall compacted through ages, each layer a delicate time capsule of atmospheric composition. Tiny bubbles trapped within the ice held whispers from thousands of years ago, allowing scientists to reconstruct temperatures, precipitation levels, and even volcanic activity across deep time. What had once been the realm of oral tradition and fragmentary historical records now expanded into a long and continuous climatic memory. Through these frozen archives, researchers traced the waxing and waning of ice ages, the sudden warming events that punctuated them, and the subtle atmospheric shifts that guided human migrations long before written history began. Weather, once perceived as ephemeral, gained a sense of geological permanence, its rhythms echoing across tens of thousands of years. At the same time, the tropics revealed their own secrets through the study of paleoclimatology. Coral reefs, built by the slow labor of countless tiny organisms, preserved in their growth rings the temperatures and chemical signatures of the oceans in which they thrived. Unlike ice cores, which spoke in the language of cold and snow, corals whispered of warm currents, monsoon intensity, and changes in salinity driven by shifting rainfall patterns. By combining coral records with sediments from ancient lake beds in Africa, South America, and Southeast Asia, scientists traced the history of monsoon systems
back through eras when continents were arranged differently than they are today. These insights revealed that far from being static, monsoons pulsed with an internal rhythm, influenced by orbital cycles, ocean currents, and atmospheric chemistry. The grand sweep of history, empires rising and falling, cultural centers flourishing and fading, often aligned with these shifts in rainfall and drought, demonstrating how profoundly weather shaped even the broadest arcs of civilization. Meanwhile, in regions closer to the poles, the Arctic and Antarctic became arenas of both discovery and concern. Researchers stationed at remote outposts endured seasons of biting cold, fierce katabatic winds, and months when the sun either refused to rise or never set. Their work illuminated the intricate dance between sea ice, air temperature, and atmospheric circulation. The polar jet stream, once thought to be a relatively stable river of high-altitude winds, revealed behaviors far more complex. Its meanders, influenced by temperature contrasts between the equator and the poles, guided the movement of storms, heat waves, and cold snaps across entire hemispheres. Subtle changes in ice cover altered the jet stream's course, sending unusual weather patterns spiraling into regions unaccustomed to them. Farmers in temperate zones began noticing erratic seasons.
While these discoveries unfolded, researchers refined their understanding of one of the atmosphere's most mesmerizing phenomena: lightning. For centuries, lightning had been both feared and worshipped, its blinding flashes and thunderous claps woven into mythologies across cultures. But modern instruments revealed that lightning was far more complex than the simple cloud-to-ground strikes familiar from summer storms. High-speed cameras captured branching filaments of plasma weaving through clouds with fractal intricacy, splitting and rejoining in patterns shaped by microscopic imbalances of charge. More astonishing still were the discoveries above the clouds. Enigmatic bursts of light, known as sprites, elves, and blue jets that flickered in the upper atmosphere during intense thunderstorms. These elusive events, invisible from the ground, danced high above the reach of ordinary lightning, extending the boundaries of the electrical storm into the edge of space. Satellites and specialized aircraft captured footage of these luminous apparitions, revealing a world of electrical turbulence previously unknown to science. The discovery that weather reached far into the upper atmosphere suggested a dynamic bridge between the sky we see and the cosmic environment beyond. As humanity's grasp of atmospheric electricity deepened, so too did its understanding of the intricate microphysics that governed clouds. Within each mass of vapor drifting across the sky, countless particles interacted in subtle but consequential ways. Dust grains, sea salt particles, and even microorganisms served as nuclei around which water droplets condensed. Every raindrop, every snowflake, and every hailstone carried within it a history of microscopic interactions, revealing how the atmosphere transformed invisible vapor into tangible forms. Supercooled droplets clung to aircraft wings, prompting engineers to design anti-icing systems capable of countering dangerous accretions. Hailstones, once mysterious in their sudden formation, were revealed through radar and laboratory studies to grow within powerful updrafts, each layer recording a cycle of ascent and descent through turbulent clouds. Even the familiar beauty of snowflakes gained new scientific richness as researchers captured their crystalline structures under microscopes, observing how temperature and humidity sculpted each branching pattern with mathematical precision. Weather, viewed upon this microscopic stage, became a symphony of physics, chemistry, and motion, whose consequences echoed across landscapes and lives. Yet beyond the atmospheric artistry of clouds and lightning lay the monumental power of tropical cyclones, typhoons, and hurricanes, the great spiraling engines of heat and moisture that patrol the world's warm oceans. With satellites offering clear views from above, their structure became a subject of intense study. The eye, a calm void surrounded by a furious wall of towering thunderstorms, resembled the pupil of a colossal atmospheric creature. Through the eye wall surged updrafts powerful enough to loft ocean spray into heights where only aircraft and the bravest seabirds ventured. Radiating outward, spiral rain bands stretched hundreds of kilometers, their arc-like structures guiding wind and waves toward distant shores. Aircraft known as hurricane hunters flew directly into these storms, gathering data from regions where no satellite could peer into the depths. They measured drops in pressure so intense that they reshaped the ocean's surface beneath them, recorded winds strong enough to peel asphalt from roads, and documented rainfalls capable of transforming mountain valleys into sudden torrents. The awe these storms inspired mirrored that of ancient cultures, yet modern science sought not to appease them, but to understand their fuel. Warm ocean waters, atmospheric instability.
Simultaneously, new branches of atmospheric science blossomed. Urban climatology revealed how cities created microclimates of their own. Concrete, asphalt, and glass absorbed and radiated heat, generating urban heat islands that could raise temperatures significantly above those in surrounding rural areas. Tall buildings altered wind patterns, creating channels where gusts accelerated dramatically and eddies where air stagnated. Pollution from vehicles and industry interacted with sunlight to form smog, a chemical haze that transformed city skylines and affected local weather by modifying cloud formation processes. Researchers began installing dense networks of sensors on rooftops, lampposts, and traffic lights to capture the fine-scale nuances of urban weather. This proliferation of data revealed the layered structure of city atmospheres, with pockets of heat, humidity, and turbulence stacked vertically across skyscrapers and streets. Weather, once thought of in terms of broad regional patterns, unfolded within cities at scales as fine as a single neighborhood. Across mountainous regions, scientists examined how dramatic elevation changes shaped local climates. On steep slopes, a valley's morning chill could give way to midday thermals that lifted gliders into the sky on invisible pillars of rising air. Mountain ranges disrupted prevailing winds,
forcing them upward into colder altitudes where moisture condensed and fell as rain or snow. This orographic effect produced rain shadows, arid regions on the leeward sides of mountains where deserts flourished not because of latitude, but because of the atmospheric barrier created by towering peaks. These same mountains could generate gravity waves, rippling disturbances in the atmosphere that propagated for hundreds of kilometers, influencing cloud formation far beyond the visible horizon. Pilots learned to avoid the powerful downdrafts associated with these waves, while climatologists studied their impact on global circulation. Mountains, often perceived as static features, revealed themselves as active participants in the choreography of weather. As the depth of atmospheric science expanded, so too did its historical reach. Researchers turned their attention to ancient climate events that left indelible marks on human societies. The collapse of the Akkadian Empire in Mesopotamia coincided with a prolonged drought evidenced in dust deposits across the region. The decline of the Maya civilization aligned with severe reductions in rainfall recorded in lake sediments and stalagmites from Yucatan caves. Even the migrations of steppe peoples, which reshaped Eurasian history, traced back to climatic shifts that altered grassland productivity. By integrating archaeology, paleoclimatology, and atmospheric models, scientists reconstructed the interplay between weather and human history at scales that across the deserts of northern China, where the winds carved loess into towering cliffs and shifting dunes, scholars pieced together evidence of ancient storms that had shaped landscapes long before the first dynasties arose. Grains of wind-blown sediment, layered like the pages of a vast geological manuscript, recorded cycles of intensifying and weakening monsoon winds, each fluctuation influencing the spread of grasslands, the expansion of deserts, and the movement of early pastoral cultures. As researchers traced these patterns across the Eurasian landmass, they began to understand how vast dust storms, known today as Asian dust events or yellow dust, had swept across China, Korea, and Japan for millennia. These storms carried fine particles high into the atmosphere, their plumes crossing oceans and depositing minerals as far away as the western coasts of North America. What seemed at first like a local phenomenon revealed itself as a transcontinental exchange, demonstrating how wind could unite regions separated by entire oceans. Ancient poets had described these storms as celestial veils drawn across the sky, but modern science showed that they were also agents of global nutrient transport, delivering iron to distant seas and fertilizing ecosystems half a world away. In Africa, likewise, the Sahara served as both a barrier and a bridge. Its immense heat generated powerful convection currents, sending warm air rising thousands of meters before drifting westward across the Atlantic. Once aloft, this dusty breath of the desert mixed with the moisture of tropical air masses, influencing the formation of hurricanes that would eventually sweep toward the Caribbean and the southeastern coasts of North America. Satellites captured these vast plumes, glowing in soft tones against the deep blue of the ocean below, and meteorologists traced how this Saharan dust suppressed or invigorated storm development, depending on its concentration and altitude. But these airborne particles bore deeper stories as well. They bore traces of ancient lakebeds, remnants of a time when the Sahara was a mosaic of savannas, ponds, and fertile shores. Embedded within the dust were microscopic fossils, diatoms, spores, pollen, whispers from the green Sahara era, when monsoon rains reached deep into the continent's north. Each storm, though transient, carried within it memories of climates long vanished, revealing that the present was only one chapter in a long atmospheric saga. Farther south, in the equatorial forests of the Congo Basin, weather manifested differently. Here, towering cumulonimbus clouds assembled with breathtaking speed in the afternoons, releasing torrents of rain that crashed through the canopy like drumbeats on ancient earth. Researchers studying these tropical storms discovered that the Congo Basin produced some of the most intense lightning activity anywhere on the planet. High-frequency monitoring stations detected thousands of strikes per hour during peak storm seasons, illuminating the forest with fleeting webs of electricity. Deep within the forest, humidity sculpted its own microclimates, cool pockets beneath dense vegetation, steam-laden clearing.
Meanwhile, along the edges of Antarctica, the southern oceans became a focal point for understanding some of Earth's most powerful winds. The roaring 40s, furious 50s, and screaming 60s, bands of latitude named by sailors of earlier centuries, were known for their relentless westerlies, winds that circled the globe with almost no interruption from land masses. These winds whipped up colossal waves, some reaching heights taller than multi-story buildings, and drove currents that played a central role in global heat distribution. Scientists deployed drifting buoys and autonomous underwater vehicles to measure temperature, salinity, and current speed in these turbulent waters. Their findings revealed the presence of the Antarctic circumpolar current, a massive flow that acted as Earth's climatic conveyor belt, redistributing heat between oceans and regulating atmospheric circulation. This immense system, set in motion by the planet's rotation and the stark temperature gradient between the poles and the equator, shaped storm tracks that spiraled across the southern hemisphere. Its influence reached far beyond the oceans, affecting rainfall in South America, drought cycles in Australia, and even seasonal patterns in southern Africa. Back on land, researchers explored how weather shaped some of the world's harshest deserts beyond mere heat and dryness. In the Atacama Desert of northern Chile, often considered the driest place on Earth, meteorologists studied rare coastal fogs known as camanchaca. These ethereal veils drifted inland from the Pacific, driven by subtle pressure gradients, providing life-sustaining moisture to ecosystems that had adapted to survive without rain for decades at a time. Using fog-catching nets, scientists harvested these delicate droplets, examining how they formed, condensed, and clung to microscopic salt particles carried from the sea. The Atacama's clear skies, shaped by stable atmospheric conditions, also turned the region into one of the world's premier astronomical observation sites. Telescopes peered through the dry air into distant galaxies, their clarity a gift of the very same weather patterns that rendered the land nearly waterless. Here, weather expressed itself not through storms or winds, but through silence, transparency, and the almost complete absence of clouds. A reminder that atmospheric phenomena could be as much about stillness as about force. In the American Southwest, the interplay of heat, terrain, and seasonal moisture gave rise to the dramatic spectacle of the North American monsoon. Each summer, moisture surged northward from the Gulf of California and the eastern Pacific, guided by shifting winds and heated desert surfaces. This influx of humidity triggered explosive thunderstorms that rumbled across Arizona and New Mexico, their anvil-shaped clouds towering above mesas and canyons. Lightning crackled through the twilight with such frequency that observers described the nights as strobe-lit, and walls of dust, hubbubs, raced ahead of the storms, reducing daylight to amber twilight as they engulfed miles of desert in minutes. These phenomena, long familiar to indigenous communities, shaped seasonal rhythms for centuries. Modern researchers, armed with Doppler radar and atmospheric soundings, discovered how subtler changes
Across Europe, the complex interactions between the Atlantic Ocean, the Mediterranean, and continental air created a mosaic of weather patterns that varied dramatically across relatively short distances. The Mistral, a fierce cold wind channeled through the Rhone Valley, could clear skies over southern France in a matter of hours, its arrival marked by a sudden drop in humidity and a whistle between narrow streets. In contrast, the foehn winds of the Alps spilled down mountain slopes with surprising warmth, melting snow at speeds that astonished early chroniclers. Scientists discovered that this sudden warming resulted from air compressing as it descended, transforming the wind into an agent capable of altering entire ecosystems over the course of a single afternoon. These regional winds, once the subjects of folklore and superstition, became key to understanding how topography sculpted atmospheric behavior. They revealed that weather, though governed by universal physical laws, expressed itself uniquely in every corner of the world. Meanwhile, the study of severe convective storms entered a new era. Advances in high-resolution radar and atmospheric modeling allowed meteorologists to peer into the internal structures of thunderstorms with unprecedented clarity. They identified rotating updrafts, mesocyclones, that sometimes gave birth to tornadoes, and they mapped the progression of gust fronts, spreading outward like invisible waves from storm boundaries. Researchers flew instrument-laden drones into storm environments once considered unreachable, gathering data on temperature, humidity, and turbulence from within the turbulent heart of thunderclouds. These insights revealed the staggering complexity of storm dynamics, where microbursts could unleash downward winds stronger than some hurricanes, and where hailstones grew layer by layer as they cycled through freezing and melting zones within the cloud. Every storm, no matter how fleeting, became a laboratory of atmospheric physics in motion, its internal processes shaping the safety of cities, the resilience of infrastructure, and the very boundaries between calm and catastrophe. Yet, even as understanding deepened, the atmosphere continued to astonish. Atmospheric rivers, long, narrow channels of concentrated water vapor, were discovered to transport more moisture than many of the world's largest rivers combined. These invisible highways spanned thousands of kilometers over the Pacific, delivering intense rainfall to the western coasts of the Americas. When conditions aligned, they produced storms so potent that entire mountain ranges groaned beneath the weight of sudden snowfall, while lowlands swelled with floods that reshaped valleys overnight. Patterns once attributed to chance now revealed themselves as components of vast atmospheric circulations, linking tropical evaporation to winter snows on distant continents. Meteorologists traced these rivers upstream to the warm pools of ocean water where they originated, illuminating how the smallest ripples in the tropics could cascade into enormous hydrological events far to the north.